Welcome to The Quantum State, a podcast exploring the latest research and innovation in quantum computing. Join us as we dive into groundbreaking breakthroughs, trends, and news shaping the quantum landscape. Hi, everyone, and welcome back to The Quantum State. Today, we have Théau Peronnin, which I'm going to ask you to pronounce your name as well, who is the co-founder of Alice and Bob. So please introduce yourself correctly now that I've butchered that, and tell us a little bit about yourself and how you got into the quantum computing space.
Thank you, Anastasia. So indeed, I'm Théau Peronnin. I'm the CEO and co-founder of Alice and Bob. I'm a physicist by training and passion, turned entrepreneur later on. I did my studies at École Polytechnique and specialized in quantum physics at École Normale Supérieure here in France, in Paris. And did my PhD actually on superconducting qubits for quantum information. And we started with Raphaël Lescan, my co-founder, Alice and Bob, right before defending our PhDs back in 2020, so 4 years ago.
Great. So tell us also, what does Alice and Bob do?
Yeah. So at Alice and Bob, we're building a universal fault-tolerant quantum computer out of a new kind of superconducting circuits called the Cat Qubits. And the idea of the Cat Qubits is really to design a qubit from the ground up for fault tolerance, for the ideal quantum computing. And the thing that is incredible with Cat Qubits, and I'm sure we're going to talk about that a bit during this conversation, is that they're able to correct autonomously half of the errors that limit the performances of a quantum computer. And by doing so, they provide a shortcut to fault tolerance that we're building upon. So at Alice and Bob, we're a hardware company. We do everything from the math, the design of the chip, all the way up the integration of the system and the firmware of the machine.
For our listeners, your team is quite interested in Shor's algorithm in particular, and that's been one of the high impact things that you've been thinking about. What do you see as the implications of that? Is it going to be useful in the future if people are shifting away from the cryptography that it potentially compromises anyway?
That's a very good question. Actually, the reason why we go for Shor algorithm as a benchmark is because Shor algorithm has several features. The first one is a historical one, and the second would be that it's a very cleanly defined use case, and the last one is that it's actually one of the toughest use case out there. So to say a bit more, so historically, Shor algorithm, came as a kind of a breakthrough. The moment in time where people started to realize that quantum computers were not limited in terms of potential only to simulating quantum physics. It was a new class of machine able to tackle problems that were, that had no other options to be solved. And so this is when quite a few physicists, mathematicians started to investigate more deeply quantum computing. Now, as a benchmark, the good thing is that when you say, well, I'm going to benchmark an architecture to see how many qubits, what are the hypotheses to be able to run Shor algorithm to break RSA 2048, well, there is nothing undefined there. You have a very cleanly defined problem, and so you can compare apples to apples when you benchmark to architecture. And then the good thing for us, from a mindset of building a useful machine, is the fact that we know breaking RSA 2048 is actually one of the most stringent use case out there. So one thing I like to say is that if you can run Shor, you can run anything. So that way you can think of this as the end goal, at least for now. I mean, computing in general is a never-ending story, obviously, but it's a good target to have in mind.
A very easy one to verify as well. Unlike
Yeah,
many
exactly. I mean, it's a good benchmark. Now, from a useful, I mean, is it going to be used? I actually hope not. But that's a personal take here. I believe for most of internet security and things like that, we'll have plenty of time to pivot away. Now, it's a known thing that many intelligence services at the moment, or not very nice players, are starting to fill up hard drives with encrypted data that they hope to decipher later on. But apart from that, I think it's more of a math problem as a benchmark. This is how I view it.
Yeah, another thing is, right, it's a pretty deep circuit. So when we talk about financial and pharmaceutical applications, VQE, these are what we call kind of the shallow circuits, in that they don't have a lot of gates in a row. And Shor's is actually a pretty deep one as well, which, kind of to your point, is if you can run Shor's, maybe you can run anything at that point. That means we have solved a lot of those issues in the hardware.
Yeah, actually, I think it's a more general statement. The fact that when you look at all the algorithm with a promise of a super polynomial or an exponential speedup, they tend to be pretty deep in terms of circuit size. And the mindset we're in at Alice and Bob is really to say, well, if you want to perform classical computers, because those are already so fast, you're gonna need a super polynomial speedup. I mean, when you compare it to modern GPUs, for example, they're just able to run so many operations per second. It's staggering. I mean, so you need that kind of speedup. Thus, you need to be able to run deep circuits, and this is why we're trying to build a fault-tolerant quantum computer so that we can get error rates that are in the range 10 to the minus 8 and beyond.
No, that's an excellent point, actually, because sometimes when we talk about Grover's algorithm and search, a lot of people actually just compare that to the worst case classical search and don't think about the GPUs and other more efficient algorithms that we do have on classical systems. And then that speed up doesn't become that impressive.
Yeah, I mean, it's I mean, with just a quadratic speedup, you need your problem to be extremely big to actually start to kick in terms of speedup. So yeah, it's not that realistic. Maybe longer term, at some point when the quantum computers will be more mature, they'll be able to take on a wider class of algorithm, and actually Grover and the phase amplification underlying it is a pretty general method. I mean, it can be applied to a very wide variety of use cases, but because it's just a quadratic speedup, it's not sufficient to justify building a machine as of today. Whereas use cases with super polynomial speedup, like chemistry or Shor or even HHL, even though I mean some conditions apply there, those are the one that drives us.
So when people talk about Shor's algorithm, they're usually talking about the factoring algorithm, but there's this other algorithm he published in the same year for the discrete log, which has relevance to breaking elliptic curve cryptography. So I wonder if you could just sort of give an explanation for a lay audience how elliptic curve encryption works and why his algorithm is able to crack that.
That's kind of a curved ball, because this one is tough. So indeed, actually, so maybe to say it simply. So Shor algorithm was designed to factor large number into primes, or at least that's how I learned it. And this is very useful when you want to break RSA, the standard cryptography. But when you look at the underlying sub-algorithm, what is under the hood of Shor algorithm, especially the Fourier transform, While it also applies to some other types of cryptography called elliptic curves, which, I mean, I'm not the expert here and I won't be very good at explaining it simply, but it relates to a pretty complex math problem where you're trying to find roots of an equation. And this use the same kind of subroutines from a quantum point of view. The thing that is fun is that elliptic curve cryptography is much harder for a classical computer to break than RSA. And thus, for example, in applications like Bitcoin, where it's used, they tend to use keys that are much smaller because when you try to think only of classical attacks, you don't need such long keys. But from a quantum computer point of view, those two are completely equivalent. So actually, elliptic curves with today's key size will be broken a bit earlier than RSA.
So, I mean, you've spoken about how Shor's algorithm is a good benchmarking algorithm, as a generic representative of what a quantum technology is capable of doing. What do you see as the fundamental roadblocks, generally speaking, and in particular, what are you doing to address it with the approaches that you're using?
Yeah, the challenge is the size and the accuracy required to implement that. And so something that is known by the physicist community for quite some time now is the tremendous amount of resources required to correct for quantum errors. Meaning that if you start with slightly faulty quantum bits and you want to get some very good quantum bits that we call logical qubits, that are composite system made out of several physical quantum bits, well, with the standard approach, you need typically a ratio of 1,000 physical quantum bit per logical one. And when you look at Shor algorithm and you put all the numbers, well, the study made by Google back in 2019, I think, showed that it would take about 20 million physical quantum bits to be able to run Shor algorithm and break RSA 2048. And this is kind of the main challenge here, because I mean, today IBM is leading the path with about 1,000 physical. So we're missing 4 orders of magnitude here to get there. Now, this is not the definite answer to the problem, and Alice and Bob is pioneering a new path, a simplification of this. The idea is to say that when you look at those 20 million required, actually only 0.03% of the qubits are here to compute, meaning the remaining 99.97% are overhead. What we do at Alice and Bob is that we make those qubits compute. And so what we've done in the past is that we designed a novel type of qubit called the Cat Qubit that corrects half of its errors natively through a hardwired feedback loop. And by doing so, we gain a square root ratio on the overhead. So we're basically left to 30 to 1 instead of 1,000 to 1. And so what we showed is that if you take all the algorithm together, you end up requiring only 350,000 instead of 20 million. So you gain a 60-fold improvement. And this is already very impactful because the cost and the complexity of the machine is somewhat directly proportional to the number of qubits. So when you gain a 60-fold improvement, while you slash the price of the machine by 98%. So it's pretty significant. But it's still, I mean, it's still 350,000 qubits. So we're not there yet. And the last result we just published a few days ago showed how to keep improving upon that. So we gain another almost 4-fold. We're now slightly below 100,000 qubit required.
Yeah, so this is a great segue into the paper. And like I mentioned, we have been discussing this paper a lot on this podcast. It's one of our favorite topics to talk about because it really kind of changed the game this year in in accelerating. I think for a while we thought that quantum winter was kind of here, but everyone was just quiet, really working on great things. So the paper is called Computing 256-bit elliptic curve logarithm in 9 hours with 126,133 cat qubits. So we mentioned these a little before, but can you go more in depth? What are cat qubits?
Yeah. So Cat Qubits are a new kind of superconducting qubits in the implementation, and then they're kind of a new paradigm, because when you think of the standard superconducting qubit, called the transmon, it's basically the most simple qubit you could think of. It's a capacitor and a Josephson junction, and that's it. It's a highly harmonic system, and the only thing you can do to improve its performance is work on material science. Increase the quality of your fabrication. Now, what we change as the mindset when designing Cat Qubit is that we realized over the past decade that correcting for errors means basically finding a way to extract entropy from the system continuously without extracting information, without creating decoherence on your system. And so Cat Qubits is a system. It's actually an almost harmonic oscillator, so an LC resonator, an antenna, if you may, where we engineer a coupling with its environment, so that we can continuously inject energy and extract entropy from the system without leaking information. And so by doing so, basically we're inventing the static RAM, the SRAM of quantum computer, in the sense that just like the SRAM, it's slightly more complex than the dynamic RAM, which is just a capacitor, but it's always powered, always stable, and it's perfectly meant for compute. So Cat Qubits, I mentioned, an antenna in which, through this mechanism, we stabilize two possible states of this antenna. Two possible states of the same amplitude but opposite phases. Just like if you would take a pendulum and drive it vertically at twice its frequency, you will see that you would stabilize two possible positions of this pendulum. Actually, the maths is exactly equivalent. And what we showed experimentally, and that was actually the beginning of Alice and Bob in 2020 in Nature Physics, and now we improved upon that pretty significantly, is that the bit flip time, the time between two errors of bit flip in this qubit, increases exponentially with the amplitude of this oscillation, with the number of microwave photons we put in the resonator, and it does so only at a linear cost on the other type of errors called phase flip. So basically, to wrap up Cat Qubits, it's a driven qubit that is able to increase exponentially its bit flip time at a linear cost on phase flip without any prefactor. So it's perfectly meant for fault tolerance, but it's terribly bad at NISQ, at noise intermediate scale quantum computing.
So Cat Qubits, the name is inherited from, of course, the famous Schrödinger cat concept. And there the idea is that you've got big physical systems in superposition with one another. And this is, I take it, how the name comes about in this case too. We've got a superposition of two quantum states, but large as far as qubits normally go. So when you learn quantum physics, the first thing they teach you is when you have a superposition of large things, it doesn't work, right? It decoheres. But here it seems that we're getting the opposite effect. You've got a superposition of two relatively large, or not quite macroscopic, but not as small as usual either. And yet it's giving us all this error reduction. How does that come about?
Yeah, it's a very good question. I mean, we could talk from there for hours, because it's an interesting challenge. So indeed, in our typical Cat Qubits, each qubit is comprising of about 10 photons, let's say, in terms of orders of magnitude. So quite a few excitation compared to your transpond that is only a box either containing 0 or 1 photon. But in some sense, this is pretty general, meaning when you want to correct for errors, and this is very general, you need redundancy. Actually, from a maths point of view, you need a larger Hilbert space that you burn most of it to stabilize a subspace of a submanifold of dimension 2. When you think of the standard approach to quantum error correction, well, the surface code is somewhat of the same. You use plenty of two-level systems that you use in harmony together to create this logical qubit, this two-level system. But at the end of the day, it's also a large macroscopic system with plenty of excitation in it. The difference in Cat Qubits is that it's extremely hardware efficient, meaning you get all that redundancy directly from a single component on your chip, because this component is a box that can contain many photons. So it's it's kind of the surprise of quantum error correction is that indeed you can get larger systems that are more stable than a smaller system.
Yeah, I mean, there are always trade-offs. Whenever we talk about any sort of error correction, there's a trade-off. So if we've got a superposition of whatever it is, a large number of photons, then you lose one of them, boom, flip the phase, or do a logical bit flip, right? So there's a trade-off in some other degree of freedom, inevitably.
Yeah, exactly. That's a very good point. So that's what I mentioned by saying there is a cost, but the cost is only linear in the number of photons. See, for a Cat qubit to suffer a phase flip, indeed it only takes the loss or the gain of one photon, and one can very easily guess that this is proportional to the number of photons involved in the Cat qubit. So as you increase the size or the number of photons, you're going to increase linearly without any prefactor your phase flip rate. But since you're gaining exponentially on the bit flip, and this can be understood as kind of two potential whale that gets further and further apart through a barrier that grows with the size of the system. And if you've done a bit of quantum mechanics, you know that the probability to tunnel through this barrier reduces exponentially with the size of the barrier. So this is how you get this trade-off. Now, for experts out there, the approach we do at Alice and Bob by correcting bit flips first and then phase flip through redundancy is kind of a Bacon-Shor like approach. So it's a type of code that corrects one errors and then the other. And this cannot get you to arbitrarily low error rate. There is an optimum, a maximum, so a limit to that. But what is good for us is that this optimum is far enough. I mean, it's in 10 to the minus 8 or 10 to the minus 9 error rate with reasonable hardware hypothesis. So indeed, there is a cost to pay, but we believe it's a very reasonable approach, at least for the first 10 to 20 years of fault tolerance.
So I know one of the really notable advantages of the Cat qubits is that you can use them to exploit the fact that noise usually has a bias. One type of noise is more common than another. And whereas with qubits, you can't keep your code immune to the bias and do processing with it. With the Cat qubits, you can. So it preserves the noise bias because you're working with this higher dimensional thing using many photons. But I was wondering, I noticed that some of the earlier work, at least from a few years ago, seemed to show that the state preparation wasn't so great. And also measurements also weren't so great with some of these codes. Can you comment on some of your strategies to improve those numbers?
Yep. So maybe to comment on the noise bias and then come to the spam error, states preparation and measurement. The noise bias, indeed. I mean, you have plenty of qubits that exhibit noise bias, meaning asymmetry between bit flips and phase flip, or T1 and T2 for experts. And the thing that is pretty unique with Cat Qubits is the fact that we have a gate set that allows us to do bias preserving gates, meaning that you can understand this pretty simply. If each of my Cat Qubits exhibit, let's say, no bit flips, but only phase flips, and I only later on correct for phase flip, I should not at any point through my algorithm be able to convert a phase flip into a bit flip, because I'm never going to catch it up later on. So I need each and every of my gates at the physical level to preserve this bias, which, for example, prevent us from implementing at the physical level gates like the Hadamard gate, because by definition this would convert a bit flip into a phase flip and vice versa. What we at the beginning of Alice and Bob, what started the company, the fact that we already had an architecture with bias preserving gates that let us build logical qubit, and then at the logical qubit level have a universal set of gates with the Toffoli plus some measurement and preparation and the CNOT gate. And with that, you can reconstruct and compile the Hadamard gate. But since you are at the logical level where you've corrected bit flip and phase flip, and you're no longer somewhat noise biased, then you're good to go. And this is pretty exciting. Actually, we in our last papers this summer, we show, at least on single qubit gate, we haven't published yet on our 2 qubit gates, that those gates are indeed bias preserving, meaning the probability of having a bit flips during a single qubit gate is down to something like 10 to the minus 6 or so. I mean, or 10 to the minus 7. I don't remember exactly, but it's very slow. It's very small. Where the probability of having a phase flip is of a few percent. Now, regarding the state preparation and measurement, well, it really depends, because again, it's biased. So if you want to prepare 0 or 1, or if you want to measure along the z-axis, meaning whether you're in 0 or 1, this you can, because you have such a great bit flip lifetime, you can get basically as many 9s as you want. I mean, you can be extremely accurate there. Now, we don't have a Hadamard gate, and we need to measure and prepare along the x-axis as well. And here, this is where we're working pretty strongly, because what we've showed is that it's this is directly proportional to the square root of the strength of our autonomous stabilization. So the more nonlinear our system is, the more able to autonomously correct its errors through this engineered dissipation, the better our gates. And we're actually pretty close to the threshold of quantum error correction. And we believe our latest chip, Helium-1 with 16 cat, will be under the threshold for error correcting code. I mean, listeners can go and read the blog post by Sébastien Jesuin, our chief of our experiment, that puts everything in perspective here about the challenge. Basically, we're not that far from threshold.
Okay, great.
So how much closer do you think this approach takes us to getting to something large and scalable, like an implementation of cracking elliptic curve, compared to all the other mainstream architectures that we're familiar with?
So the way I like to view it currently is to say, cracking elliptic curves is a bit further down the road. The question for me is, when do we start outperforming classical computers at a wide variety of tasks that is not just Bose sampling or simulating a quantum system with a quantum system? It's kind of a tautological problem.
It's a bit of a cheat, isn't it? It's a bit of a cheat. We say it simulates itself.
Yeah, exactly. So that's not very impactful. For me, the right target, the moment where quantum computers start to be in orbit, if you want to build the analogy with the space race, is when you get about, between 50 and 100 logical qubits with error rate that are low enough, meaning lower than 10 to the minus 6, at least. And this is when you can start running algorithm for deep physics, for example, for simulating spin chains or things like that. When you have a machine that becomes relevant for researchers and scientists out there. And so what we showed with our latest LDPC plus Cat architecture, so low density parity check that I mentioned before, where we gain another 4-fold improvement, is that we could build 100 logical qubits with a rate of 10 to the minus 8 with as few as 1,500 cats. And 1,500 cats is something IBM is close to be able to manufacture. So our internal roadmap, for example, aims at delivering such a machine in 2028. And from there, well, it becomes commercially viable, and you can scale from there and get to elliptic curves, I don't know, a few years later, I guess. But with our novel architecture, I guess elliptic curves would take something like 40,000 cats to run, and Shor slightly below 100,000 for RSA, sorry.
So can you go a little bit more in depth? You kind of alluded to this new paper that was just released a few days ago, maybe a week ago. So can you talk a little bit more about the key findings of that and what helped you kind of move to this next stage of development?
Yep. So our previous architecture was extremely naive in some sense. You correct natively for bit flips, and then you use the most naive error correcting code for correct classical one, because you only have one type of errors. That is the repetition code, just basically a chain of cats where you do a majority vote to correct for errors. Now, we knew for quite some time that there are more advanced classical error correcting code that can be applied here. So we worked on a type of codes that are called low density parity check, that are used, that have been invented in the 60s and that are used in plenty of today's technology like 5G or Wi-Fi, I believe. Sorry. And the finding that something we realized is that combining cats with LDPC codes works tremendously well, because people have been looking at LDPC codes for quantum computing for quite some time. There is a beautiful paper by IBM released last summer on that. And the thing is in the paper is that the promises are great, but the engineering challenges are pretty daunting, because it takes a special kind of connectivity. You need to be able to connect qubits that are pretty far apart from one another. So this complexifies the design of your chip quite significantly. Plus, it's not very clear how you can run gates on such code. So it's I think their paper is titled Quantum Memory and not Quantum Processor. Here, what we showed is that because Cat Qubits only leave one type of error, you can use not a quantum LDPC code, but a classical LDPC code. And this lifts quite a few no-go theorem of maths. And more precisely, we show in this paper that we can achieve not only a 4-fold gain on overhead, but also be able to run gates, and also do so while only requiring local, nearest neighbor or next nearest neighbor at most connectivity, which is something that is, currently pretty mundane in superconducting circuits. So the finding of this theory paper is that we have an architecture feasible with today's technology that opens a path to get to those machines of 100 logical qubits and more pretty soon.
A little detailed question on this, because I found this very interesting using the LDPC codes. So many of them have a structure that has a symmetry under translation, so the way the code is structured. And so that, like, sort of a natural for a system with periodic boundaries. So how can you get around that issue with your architecture? Do you have a workaround for that?
Oh, yeah, this might be slightly beyond my ability. I'm gonna need the team here. Something I can comment on is the fact that actually the type of because LDPC code is actually a family of codes. It's not one given. But the one that work best on our architecture are actually called a subfamily of cellular automata. So basically, small packets of error correcting code that you propagate on it. So this kind of echoes this translational invariance you mentioned. And indeed, there are boundaries condition. But here, you're going to need to invite my chief of theory, Jeremy Guillot, to get a more detailed answer.
No, it's quite a fascinating result. It's nice to see that some of the really well studied advances in classical computing actually can be made to work in a quantum regime by using some very clever ideas, like you've managed to use this larger space of photons to encode quantum information. And yeah, that's quite nice.
Yeah, now the challenge is on the experiment side, because having such a nice architecture is a driver for the team. Now it's great promises that we will be able to claim victory once the chip is actually running that error correcting code. So currently we're working on a prototype of logical qubit, still using a repetition code with our 16 cat called Helium-1 that will be communicating more about this year. And then we'll move on to a bit more than 40, where we'll be able to have a very long-lived logical qubit, and also start demonstrating the LDPC plus CAT architecture, and later on move to large-scale machine that can actually deliver impact on real use cases.
I'm curious also, have you thought about using your architecture for material design? So, maybe either synthesizing new materials or running simulations that are just beyond what classical computers can do, but also aren't so complicated that you would need hundreds of thousands of qubits.
Yeah, so my understanding of those algorithms, actually, the team is currently working on the detailed resource estimation there to provide numbers. But my understanding for material science and chemistry in general is that indeed you need fewer qubits, and it starts to kick in at a few hundreds of logical qubits. But the challenge at the moment is that you need even better fidelities. I mean, to deliver impact, you need fidelities that are pretty good, in 10 to the minus 11 or more. The difference with an algorithm like Shor is that here you can actually average in some sense, and so you can have a trade-off between time and space in some sense. So this obviously is not a favorable scaling, but it can let you grab the last few orders of magnitude that you're missing.
What do you see as the single most important issue that quantum computer scientists need to be working to overcome for the future of the field? I guess my understanding is you're focusing on error correction to a large extent in a pretty novel way. What do you see as the really big issues?
So there is something that I mean, Google and us start to encounter, because when you get to longer lifetime, actually what you have is a more sensitive probe. And so you start probing events that are more rare. And more precisely, one of the challenge that we might encounter, it's still a bit soon to say, but at least this is part of what keeps me up at night, are the source of correlated errors. And here's kind of story time. So I don't know if you remember the catastrophe of Fukushima. At Fukushima, they had 4 water pumps for the primary circuit. And so this ensured redundancy, and they said, well, the probability of one failure is low, but the probability of all 4 pumps failing is extremely, extremely low, so we're good to go. But the problem was that all the 4 pumps were in the same room, and when the tsunami hit, the whole room was flooded. So you had a correlated error here, and this led to the catastrophe. And this is true for every code out there. They are meant to correct for uncorrelated errors. So once you have a source, let's say, imagine a meteorite that hits my chip. I'm going to have a correlated error on all my qubits, and I'm not going to be able to correct that. In our case, it's not meteorite. It's likely to be high energy physics like muons or things like that hit the chip every 10 seconds or 100 seconds and create phonons all over the chip, which leads to correlated errors. So this is something we're working on. We have quite a few ideas on how to correct that. But yeah, as you start getting to longer lifetime, longer coherence time, you start encountering novel physics, rarer events, and those will need dedicated engineering tricks to circumvolute.
So you've alluded a little bit to your roadmap and timelines, but I want to ask you the million-dollar question we always ask is, how far away are we from seeing quantum computers actually solving a real-world problem that a classical computer can't? And also on your end, what you think that will be when we can actually break encryption, let's say, in a reasonable amount of time before the heat death of the universe?
So today I'm pretty confident that quantum computer will become useful in a regular basis before the end of the decade. Meaning, as soon as you start having those hundreds of logical qubits with sufficiently lower rates, and I mean we're well positioned, but we're not the only one on that race. I mean, you've had some terrific results by QERA, for example, and they have their own engineering challenges. But I mean, you have improvement across the board of platforms for quantum computing. So it seems unlikely that we'll stumble completely and won't be able to run that. Sorry for the double negative here, but you see my point. We target 2028 for such a machine. But if we're a bit late, I'm pretty sure it's still going to be before the end of the decade. Now, to break encryption, it's a bigger problem. But if you assume sort of a Moore's law of the number of qubits, that should start falling in, I don't know, 2033, 2035, something like that.
So what do you envision as the next big breakthrough in quantum computing? Or maybe what do you think should be the next big breakthrough?
Yeah, so two types of answers there. I think we're still missing the Sputnik moment of quantum computing. But this is not the breakthrough I want to answer. So, but first, let me say a word about this Sputnik moment. Sputnik was a useless milestone in some sense historically. I mean, it's a machine that just went out there and beeped in space for 3 months or so, but it signaled that mankind had made a machine that could escape gravity, at least for some time, and that triggered the beginning of the space era in the 60s. Now, for quantum computing, we're still missing the Sputnik moment in the sense escaping the coherence, having a man-made machine that is completely decoupled from the rest of the universe, that has no causal link with our classical world. So a proper logical qubit, and that would be a strong trigger. Now, this is going to happen in the next couple of years, I'm pretty sure. But this is not really a breakthrough in terms of something we haven't foreseen. What I'm hoping for, and I think there's plenty of room for that, is a completely new class of quantum algorithm. Because at the moment, we're still relying on the same handful of quantum algorithm. I think there was just one new that appeared in 2022, but with no clear application yet. But when you think about it, there has been so few people working on designing novel quantum algorithm compared to classical algorithm. So there is a ton of room for brilliant ideas in quantum computing here. I think we could be very surprised to see novel algorithm come forward. And again, if you do the historical parallel, and you think, this famous quote by the CEO of IBM in the 40s, that there is maybe a world market for 5 computers. It's kind of the same here, because if you thought about computing in the 40s, you were saying, well, I want to break Enigma, I want to decipher codes, and I want to compute trajectories for ballistic, basically. And you didn't have that many more ideas on what to do with a computer. History proved them so wrong, and I think it's going to repeat itself with quantum computing.
Looking back at your own history, what's been the biggest unexpected thing you've come across?
The trajectory of Alice and Bob and myself is the story of so many good stars aligning. It takes quite a bit of luck for this to happen. Not saying that we have succeeded at anything, but at least to create this opportunity. So what surprised me the most is the level of support and engagement, and how many of the physicists that were surrounding Raphael and myself while we were PhD students that jumped in the adventure with us. Not only the researchers, but also the institution, the academic labs, even at the political level, all being so supportive. That was pretty surprising. I expected a tougher time hiring the team initially, but we ended up with a pretty nice lineup of physicists, and we managed to have everyone on board.
So our listeners are academics in the quantum space, but we also have a lot of people who are students that are really interested in getting into quantum computing, or people from different domains that are thinking that quantum is going to be really important to their careers. So what advice would you give to someone starting out in the quantum journey?
I think it's about reading a lot, and reading a lot of very different things, not only scientific papers, but also get a sense of the dynamic of the whole ecosystem. And this helped me quite a lot at the beginning of my career, when I was still a student. Just to I got in quantum computing by reading IEEE Spectrum at the time, and seeing the first, pop science article about quantum computing, and seeing the momentum grow, plus the Nobel Prize of Serge Haroche and David Weinland in 2012, and kind of understanding the momentum and the dynamic. When I was a student there, in 2012, 2013, actually my peers were all learning about machine learning, and they are now starting companies like Mistral in France. I think now is the right time to get into quantum, to be in 5 to 7 years the one starting the quantum Mistral company, or the quantum OpenAI in some sense.
And just to finish up, can you share maybe your most memorable moments while working with Alice and Bob?
It's going so fast. There are plenty of great times, but I think what moved me the most was is this September, when we had our internal conference, followed by an offsite, and this is when I realized that Alice and Bob was no longer just my project with Raphael. We're now 80 people, so many things happening, seeing all those projects internally that some of them I was not completely aware of, got surprised by plenty of results. It was extremely moving to see this group, this company becoming something somewhat independent of myself, and yeah, that was moving to see the collective and the team play there as well.
Great.
So thank you, Theo, for coming on the podcast. Where can we find more information about your papers, publications, your personal social media, if you have that?
Yeah, you can follow us on LinkedIn, Twitter, or X, should I say. The website is alice-bob.com, and we publish everything we do on archive. So yeah, no secrecies there. Go and have fun. Cat Qubits are very new, and bosonic system in general. There is plenty of room for research, and don't hesitate to reach out. Happy to collaborate.
Great. And for listeners, thank you for listening to this episode. If you are on YouTube, make sure to comment down below if you have any questions, any guests you'd like to see, any follow-ups, we can bring people back. Make sure to like and subscribe on Apple or wherever you get your podcasts. And thank you so much, Peter and Gavin, for joining as well.
Thank you. Thanks,
Thank you.
Theo.
Thanks a lot for having me.